Alrighty guys, we're going to go ahead and get started with our work notes. So some of you might be asking yourselves, what is work? Well, I'm going to tell you what that is. Work in physics is the transfer of energy from one form to another by a force. Specifically in physics, we're going to say that it's the energy transfer is either into or out of kinetic energy. And therefore there can be positive work done, and that just means that we're putting energy into kinetic energy. Another way to think about it is saying that we are receiving energy from its surroundings. So some object is receiving energy from some force. And negative work, well, negative work is going to take energy out of KE. So it's going to be the opposite, where instead of receiving energy, we're going to be giving energy to its surroundings. Now we're going to talk about the work equation. And the work equation is pretty simple. It's W equals F times D times cosine theta. W is going to stand for work, and work is measured in joules because work is the transfer of energy and energy is measured in joules. F stands for force, and it's the force that's doing the work. And we'll talk about that a little bit more later on how forces do that work. D is going to be the displacement force is exerted over that object. So in simple terms, just the distance that the force is acting over. And cosine theta, well, this is actually like kind of easy, but also really difficult to understand. And cosine theta is the angle between that force and displacement vector. And it's going to tell us whether work is positive or negative, or in some cases zero. And we'll see that on the next slide. So let's take a further look at this cosine theta. So here we have two vectors, a force vector and a displacement vector, and they're both pointed in the same direction. Therefore, the angle between them would be 0, meaning that cosine theta is equal to 1. Because cosine of 0 equals 1. We're using degrees here, obviously, because we're in physics, and this just tells us that positive work is being done by the force. Now, if we had force pointing one way and displacement pointing the other way, we're going to notice that the angle between these is 180, meaning cosine of 180. That's going to equal -1, which is going to tell us that we have negative work being done by the force. And then lastly, we have displacement pointing to the right and force pointing up. The angle between these is 90 degrees, and cosine of 90 is equal to 0. Therefore, that means that no work is being done by this force. So let's take a look at an example really quick where we try to identify what forces are doing work. So we have a person pushing a box, so we have a force applied to the right, and then there's also going to be some friction pushing back on the box to the left. We notice that the box is on a surface, so we're going to have force normal pointing up, and then also the box has mass, so we're going to have force gravity pointing down. We can see that force applied and the displacement are in the same direction. Therefore, we can say that force applied is doing positive work and transferring energy into kinetic energy. And again, that's because force applied and displacement are pointed in the same direction. The angle between them is 0, so cosine of 0 is 1, which means we have positive work. On the flip side, we have force friction pointed in the opposite direction. So the angle between force friction and the displacement is 180. We just said on the last slide, cosine of 180 is equal to -1, which means that force friction is doing negative work, and it is transferring energy out of kinetic energy. Again, we can just see my little force vectors that I put right here showing that. We also have two more forces on our diagram. We have force normal and force gravity. We're going to notice that force normal and force gravity are both perpendicular to displacement, meaning that they create a 90-degree angle. And we know that a 90-degree angle is going to result in 0 work being done by that force. So if we just think back to what we said on the first slide about positive work, meaning that we're receiving energy from its surroundings, that would make sense because the person is pushing energy like into this box, so the box is receiving that person's energy. But if we think about negative work, where negative work means that we're giving energy to its surroundings, you can see that forced friction is really giving energy to its surroundings because it's taking energy from this box and converting it into thermal energy, and thermal energy is part of its surroundings and not the actual box itself. Let's take a look at an example now with some numbers. So here we have a 1 kilogram rock that is being dropped from 10 meters. The GPE at the beginning would be 98 joules, and we're just figuring that out because we know that GPE is mass times gravity times height. So 10 times 1 times 9.8. The KE at the beginning is going to be 0 joules because it's at rest. We said it was being dropped, which means it's at rest. Velocity is equal to 0 meters per second because kinetic energy is 0. Here's our energy pie chart showing that GPE is 98 joules and KE is 0 joules. At the end though, right before it hits the ground, all of that GPE is now taken out and we're left with 0 GPE because we have no height at the end, and it's all transferred into kinetic energy because our ball is moving very quickly before it hits the ground, and that's 98 joules of kinetic energy. Obviously in this problem, we're assuming that there's no friction or air resistance, and that's why all of our GPE is being transferred into KE. So now that we know what our energies are, let's try to identify the work being done by forced gravity. Well, we know that forced gravity points down, and we know that the rock is moving downward. So those are moving in the same direction. So let's recall that work is equal to force times displacement times cosine theta. The force in this case is Fg, and now we can go ahead and start plugging in our numbers. Work is equal to, well, forced gravity is just mass times gravity. The mass is 1 and gravity is 9.8 times d, which is the displacement. It says the rock is dropped 10 meters, so 10 meters is our displacement, times cosine theta. Theta is the angle between the force and the displacement. They're pointed in the same direction, so that angle is 0 degrees. All we do is just go ahead and simplify. We find out that work is equal to 9.8 times 10 times 1. And that's because cosine of 0 is just 1. That tells us that the work being done by forced gravity is positive 98 joules. So we can just say that as the rock falls, positive work is done by gravity. This work transfers 98 joules of energy from GPE into KE. And if you're ever confused if it's positive or negative work, just remember that positive work is going to put energy into kinetic energy. So if we're ending with more kinetic energy than we started, that means that some force was doing positive work on our system. And if we're ending with less kinetic energy than we started, that means that some force is giving energy to its surroundings. Let's take a look at example number 2. We got our good old friend Mario over here trying to hit this block. Maybe he'll get it. Nah, I don't think he's going to get it. So we know that Mario is 50 kilograms. He jumps up to hit a block that is 10 meters in the air, but only jumps 3 meters high. So this is a classic example of me giving you more information than you need. So we need to make sure that we can identify what's important information in this problem. Well, the GPE at the beginning of this problem is going to be 0 joules, because we're going to say that the beginning is when Mario's on the ground and his height is 0 meters. So KE at the beginning is 1,470 joules. Some of you might be asking, Mr. Weiss, how'd you figure that out? Well, I'll show you in just a few minutes. So if we draw our energy chart at the beginning, we have 0 joules for gravitational potential energy and 1,470 joules for kinetic energy. We're going to say that the end of our problem is at the apex, right? His maximum height. So our GPE is 1,470 joules. Therefore, all of our kinetic energy got transferred into GPE, which means that now we're left with 0 joules of kinetic energy. Like I said, the GP at the end is 1,470 joules because my height was 3 meters. So now maybe you guys understand where I figured out that kinetic energy was 1,470 joules. It was because I solved for GP at the apex and knew that that energy had to come from somewhere, and it came from my initial kinetic. Final kinetic is just 0 because again, we are at the apex and we are not moving at the apex. Let's take a look at the work. Work equals force times displacement times cosine theta. The force in this case is force gravity that we're looking at. We notice that force gravity points down, but the displacement points up. So these are pointing in opposite directions, meaning that the angle between them is 180 degrees. Plug in our numbers here, we get 50 times 9.8, mass times gravity, times 3, which is our displacement, times cosine of 180, because the force and displacement are pointed in opposite directions. Because it's cosine 180, that's going to give us -1, which is just going to tell us that we have negative work being done here. So work is equal to -1,470 joules. What does this mean? Well, it just means that gravity is doing negative work and transferring energy out of kinetic energy, and it is putting it into GPE. The force is opposite the direction of motion. So if we look at what we said before about negative work, it's taking energy out of kinetic. And that's exactly what happened here. We ended with less kinetic than we started, so we did negative work. So let's quickly recap some important topics that we talked about. Positive work is going to put energy into kinetic energy. It's also a way of saying that we are receiving energy from our surroundings. Negative work is going to take energy out of KE. In other words, it means that we are giving energy to our surroundings. And lastly, forces acting perpendicular to displacement do 0 work.